What's pumping big bubbles through a column of heavy oil and rolling wheels got to do with science or common sense? Well, it's the Science Museum, and the location is called Launchpad. The idea is to let children experience the physical world in the form of a direct encounter. It's quite amazing that it takes so much effort to push a bubble of air when it's going through oil. It isn't only for children. Anyone can have a go. But it's been designed with children in mind and seems to give them plenty to do. Sitting down with one of the area's organizers to have a scientific conversation is just another experience.
Is that metal?
No.
Why not?
Because it just doesn't feel like metal. Because metal's usually cold, sort of.
Right, okay, let's give this to Ross. What do you think, Ross?
It's too light to be metal.
It's too light, okay. Stop there.
Anthony Richards is trying to give them the experience of density through solid cylinders of very different materials, and at the same time to discover their underlying beliefs and assumptions.
Metal.
Metal? Because why?
Heavy, very heavy.
Very
It's very, very heavy. Yeah.
And it's sort of cold.
These children are 10. They've had a few years to think about these things.
Be very careful.
But where do their ideas actually come from? And how scientific are they?
From the very early days of children's lives, they have experience of phenomena in the world around them. When they're sitting in a pram, they can let go of a toy and they note that it certainly doesn't go up, it falls down. From simple experiences like that, children develop informal theories that help them predict what's going to happen next, that enable them to act in the world around them. But that doesn't necessarily mean that they're consistent with the formal theories of science.
Children's understanding of many things can be discovered, to some extent, by their drawings and conversation. In an Oxford school, Teresina Nunes, a researcher into what's called naive physics, is doing just that.
Do you know what the Earth looks like if you were up in a spaceship very, very far and you were to look at the Earth? Do you know what it would look like? Yes? Yes, draw a picture of that for me, please. Yes, of the Earth. What it would look like if you were very far away, like an astronaut, looking at the Earth.
Asking children to draw the Earth will show us what they know of planetary motion and the solar system. Jimmy seems to have no doubt that the Earth is round, though a younger child might have drawn it flat. But where does this idea come from?
Children develop their conceptions both on the basis of what they think and on the basis of what they learn. So you can see that they all draw the Earth as somewhat round, but then they add their own views to it, and they have all the people standing up in one particular direction. They have mostly the clouds on what they call the top, and the rain falling always in the same direction instead of having a conception of the atmosphere all around the Earth.
Talking to the children about their drawings of the Earth, or Earths, reveals some interesting ideas.
Now, Robert, this is your drawing of the Earth that I asked you to do for me. Can you tell me a little bit more about your drawing? What did you put in?
That's some people.
That's some people.
And there's see them little lines?
Uh-huh.
They're the little bits of rain.
Did little bits of rain, I see. And where are the clouds did you put in?
There's some up there.
You have some up there.
One
One there. That's right. And that's one too, isn't it?
Yeah.
That's right. Now tell me something. Can you explain a little bit to me about the day and the night? What's the difference?
Well, the night is dark.
The night
the day
is
is
dark.
light.
That's right. And where does the light come from?
Sun.
The sun. Now, with the sun here, is it going to be day all over the world at the same time? Yeah? And how is it going to become night then? What happens when it becomes
Sun
night?
go in.
The sun goes in where?
The clouds cover it up.
The clouds cover it up.
Although clouds do often cover the setting sun, night is caused by the rotation of the Earth. Children aren't alone in believing in what they see.
I used to say that most people believe, in fact, that the Earth goes round the sun, and it turns out on surveys, only about 70% of the British public believe that. And I don't blame them. I mean, you can see, after all, when you get up in the morning, that it's the sun going round the Earth. And I think it takes quite an intellectual leap to realize that the contrary is true. What's more, even those people who do believe it, if you said, now look, why do you really believe that it's the Earth that goes round the sun and not vice versa? I think they'd be very hard put to give you the right explanation. A great deal of what we take as scientific knowledge comes by authority rather than understanding.
Much of this authority derives from learning at school. But children will know some things even if they never go to school, things they've learned from their interaction with the physical world, like playing with balls and baskets.
Okay, now all of you have a paper like this, don't you? And you know you were running outside and you had to drop a ball as you were running, non-stop. Just drop, not throw, and try and get it in the basket.
The fact is that a ball released by a moving person has the same forward momentum after its release as it had the moment before.
One of the interesting things of science is that children can conquer tasks which they don't really understand. They can carry out activities without knowing exactly what they do. And in order to get the ball in the basket, they have to let it go slightly before they get to the basket. But when they chose, in the pictures, most of them chose only the one that was dropping the ball right over the basket. Now this is the picture. These pictures are about people running and doing the same thing. You see the ball in the hand? Yeah. Now I want you to do for me. Now I want your opinion, okay? You will tick the one that is going to get the ball inside the basket.
There are two things that people get wrong very often, particularly children. In fact, Aristotle got it wrong completely. First of all, he thought that in order for an object to move, there had to be a force on it acting constantly. So he thought that when you took something and threw it, you impressed a force on the object. And of course, that's not true. When you take something and you throw it up into the air, the only force acting on it is gravity.
Forces certainly aren't easy to understand.
Now, where is this force working? Is it on the hand or on the ball? Because you put the arrow there and I don't quite know.
It's the kind of the hand and the ball because it's in the hand which is holding it up from the gravity. Then when you let go, it goes down.
Oh, I see. So it's both in the hand and on the ball because the hand is holding it from the gravity. And when you let it go, it goes down. Yeah. And how about in this picture up here? Mm-hmm. The man is running across and holding the ball, but not letting the ball fall. Are there any forces there in that bit?
I'm not quite sure.
You're not quite sure. Is there any force that could be working, do you think?
There could be.
It took nearly 2,000 years from Aristotle to Galileo before people began to get any real insight as to the rules that determine how objects move. And it came as really quite a surprise. So moving objects, we're quite good at throwing balls and so forth, but there are laws to get it down to the basic laws and rules that determine how objects move. That takes tremendous imagination, a lot of hard thinking, and you can't do it by chance.
Many of the phenomena of the physical world which we understand well enough to live with are quite difficult to explain. The evaporation of water, for instance.
Now hold it up. Hold them up. Yeah. Okay, now put your kitchen roll back on the table carefully, not on a wet patch. Not on a wet patch. And then take your hands off the table, and then we're going to leave them there. And then we're going to come back to them later.
After an interval, the children are asked to explain where the water has gone. The researcher is the Open University's Ken Richardson.
What's happened? What's happened to it? Yes, Tom?
It's dried up and disappeared.
It's dried up and disappeared.
It's soaked into the towel.
Soaked into the towel, yes. Any other answers? What's happened to the water that was on your palm print?
Dissolved.
It's dissolved.
It's
Yes.
dried up, but it's still left a mark.
It's dried up, but it's still left a bit of a mark. Yeah. All right. Now, what I'd like you to do now is do a drawing of what's happened to the water from your palm print. Can you do that? Do a drawing of what you think's happened to the water.
There are a number of ways in which children's informal theories differ from the theories of scientists. One is that children don't necessarily articulate their theories at all. They have difficulty in saying what their theories are. They are informal, often unspoken theories that guide the things they see and the things that they do without them being able to put them into words necessarily.
So even with a drawing, it's quite difficult to discover children's theories.
We have a look at your drawing now. Can you tell us what you've drawn here?
My hand.
Your hands, yes. Anything else? Does your drawing show what happened to the water?
Disappeared.
Just disappeared. What do you think happened to the water?
Dissolved.
It dissolved. What does that mean? Where did it go when it dissolved?
Inside there somewhere.
You think it went inside the paper somewhere? Yeah. Will it stay there for good? Do you think? No. What'll happen to it next?
Dry up.
It'll dry up. What happens to water when it dries up? It goes away. Yeah. Where does it go away to? Yeah, and what makes it go away? Do you know? Can you think?
It gets warm.
Yeah.
Go in your mouth or something. It goes away.
It gets warm and then it's...
Mouth or something like that, and it goes away.
Yeah, I didn't catch the middle bit. It goes mount or something like that.
Mount.
All right. And then it turns to rain.
No, and it goes away.
And then it goes away. Right. Does it
Children generally try to provide adults with the words they think they want to hear. But explaining the same thing differently at different times is also quite okay.
If a particular informal theory fits in a particular circumstance, that is fine. If a different theory fits in a different situation, that's equally fine. Children don't necessarily try to make those consistent.
But although children are not often consistent, their explanations do have some common characteristics. Like Aristotle, they often believe in the necessity of an active agent, often with human attributes. A vacuum sucks, for example.
If you ask them to explain how you drink milk through a straw, they will tell you it's because I make a vacuum in the straw and this sucks the milk up. The vacuum has this positive ability to be able to suck.
Now, the question is, what makes the water go up into the straw? Now, could you write it down and do a drawing? All right.
Later still, and probably as a result of teaching, children adopt the view that there is air on the outside at a certain pressure and the air on the inside of the straw is at a lower pressure, and the result is that there is this movement of milk up the straw.
Now, Isabel, you're going to tell us about your drawing. Can you show us what you've drawn?
That's the straw.
That's the straw.
And there's the water.
Oh, that's the water. And what have you written about what makes the water go up the straw?
The word is suction. When you suck, it pulls water into your mouth.
I see. Right.
So for Isabel, vacuums suck and suction pulls. Using a syringe to investigate air pressure, one might think, would break the connection with the human activity of sucking. But the common sense, anthropomorphic terms persist.
Right. Can I have a look at your drawing then, Paul? You got any water in your drawing?
Yes.
That's
And
the
the
one.
water syringe.
The water in the syringe is where?
Just up there.
Just up to there, yes. Now, how does the water get into the syringe?
Well, hole goes up this little hole here.
Goes about the hole there.
Yeah, and the rubber part makes it come up.
Right, so the rubber part makes it go up through that hole, does it?
Yeah,
So
and just sucks it up.
So how does it suck it up?
Well, I think it's got some things on the bottom of the
Yes.
rubber part. The rubber part makes it come up.
What sort of things, do you know?
It's got nothing on it.
Yeah. It's got nothing on it, so how does that make the water go up?
It's probably that makes it pulls it up.
It pulls it up.
Paul is only momentarily surprised by his failure to find any things on the bottom of the plunger. But science lessons could lead him to see it as an interesting problem.
In the scientific concepts, there is a search for coherence, which is much less clear in children's thinking. Children will be much happier with inconsistencies in their thinking than scientists will be.
I think there's a very big difference between scientific thinking and common sense. Common sense is about natural expectations. It's what you learn from everyday life, as it were. Scientific thinking is a rather self-conscious approach to the world. And it just so happens that the world isn't built on a common sense basis. It's nobody's fault. Again and again, you come across ideas that just totally against your expectation. It's very irritating. And when you go to really complicated things like quantum mechanics or cosmology like the Big Bang, I mean, common sense breaks down completely.
Scientific ideas have to be taught. Formal scientific ideas have to be taught. They don't develop spontaneously. Now, the reason for that is that the ideas of science include concepts and theories which are, in a sense, imaginative constructs developed by the community of scientists. They are not entities that you discover by looking at the world. Ideas such as genes and chromosomes, energy, magnetic fields, these are not things that you see in the world around you. These are constructs that have been developed by the scientific community. Now, as a result of this, children can't be expected through their own experiences to invent those ideas for themselves.
Children do gradually acquire more scientific concepts as they get older. In a century where scientific and technological explanations abound, this is unsurprising. But while the effects of teaching are easy to detect in the use of specialized terms, for example, a lot of other ideas continue to coexist. These girls are 9 years old and are investigating flotation. The boys that follow are 12.
I find it quite light. What do you think? Try it out, Nina.
Plastic doesn't usually sink. It's wax. Yeah, it's wax.
Wax. Wax doesn't usually sink. And how about the marble?
Yeah, that would, because it's glass.
You're pretty sure of that one, aren't you?
Yeah.
You too? Okay. What do you think is heavier, this or this needle? Hold them up. Hold them up. Try it out.
That's heavier.
That's heavier. But you said that is going to float and that one is going to sink.
I think metal's a bit heavy.
Oh, I think metal's a bit heavier. When we interview children, very young ones tend to concentrate on the external aspects of objects and the appearances. Children at about 7 or 8 start concentrating on other aspects of the objects that are less obvious, like the weight and what they are made of. And a little bit later, they start thinking that objects are made with more air or with less air inside them. And that is actually a precursor of the idea of density. Now, tell me something. Why are these float? Why does plastic float and wood float? Why?
Well, air can keep it afloat.
The air can keep it afloat. Where is the air that keeps it afloat?
All around it.
Around it. But why is it that the air keeps these afloat and doesn't keep bees?
Can't because of its shape, because that one's small.
It can't be because of the shape, you said. So why could it be? What do you think?
Could be because of the shape, because that's long and roundish, and that's long and round.
Long and roundish.
So this one's round, and that one's round and it sinks. Yeah, but it's not long.
And now the 12-year-olds. They have a rather original theory about why a needle sinks, but they too are basically looking for air trapped in the objects.
We think because it's got a hole in here, the water will get through.
Right.
Since it's heavier on this side, it will weigh itself down.
Okay.
It'll just sink
And
down
it would
like
just
that.
sink down like
There's
that.
nothing to keep it up.
There's nothing to keep it up, really. This is too thin.
There's nothing to keep it up.
No edge.
Or like what? What could keep it up?
In this one, you can trap air underneath.
Okay, so there might be air underneath. So you said that the car would float.
Yeah.
And you decided it would float just because it would trap air underneath.
Yeah, trapped air.
The boys test their objects to see if their predictions were correct. They have some difficulty explaining why a rubber band floated rather than sank, but the memory of a technical term helps them out.
Why is that a floater rather than a sinker?
Well, some of it seems to be staying above water because it's kind of a strange shape.
There's some sort of thing over the top of the water, which I can't remember the name of, and I don't think it's heavy enough to break it.
What,
Maybe.
like some film on top of the water?
Well, the
There's
meniscus.
a special name.
Yes.
Meniscus.
The meniscus. It can't break the
I don't
meniscus.
think it's heavy enough to
All
break
right.
it.
The boys' understanding is still incomplete and may remain so.
Might be some.
I don't think the children are all that different to us. For many issues about the nature of the world, there's a 5-year-old child really describing or thinking or giving us the explanation of how things work. So I don't think children are that peculiar. I think that there's a great deal of our thinking, like that of Aristotle's, which is very similar.
So when adults are questioned about their scientific understanding, they often answer in much the same way as children.
So you pick that one up, let's see what happens. So how would you explain the difference between those two? How would you understand the difference between that metal and this metal? Saying that they're both the same size but the same shape?
Density.
Right. How would you explain that?
I wouldn't know how to.
Right. Any offers?
No idea. Just that it's heavier and density. Yeah, I have no idea how to explain it to someone.
What is learnt at school, like the word density, is often the end of our scientific knowledge. Common sense makes up the rest of what we know. Only now and again, as adults, do we take the opportunity through play, like children, to confront our naive ideas.
Right, that's good. That's good so far. Try our luck that way. Somebody going to catch it if it falls. Well, that's... I reckon that's fair. That's nearly excellent, isn't it?